Hi, I'm Shirley. I'm a third-year CSE PhD student at University of Washington UB Lab, and I'll present LuckyChirp today. LuckyChirp is a contactless opportunistic respiratory tracking solution for commodity devices using Sonar. Providing effortless daily respiratory monitoring can offer insights into users' long-term health and potentially predict condition onsets, such as cardiopulmonary arrest. Currently, there are two ways to monitor respirations. One is to let the users to wear a chest strap to monitor their respiration. And another way is to contactless monitor the respirations by tracking the chest movement using sonar or radio signals. Since Sonar is widely accessible on commodity devices, such as smart home and smartphone, and it does not need additional hardware like RF transceivers, it is a promising way for daily respiration monitoring. So in general, existing systems sensing solutions either require the user to put on a wearable or require the users to manually start the sensing procedure. This adds user effort and as a result, usually has a high dropout rate. In contrast, we aim to provide a system that can operate in the background and does not require any user attention once set up. It automatically detects the user's respiration when they are present and static. We aim to provide an accurate respiratory rates monitoring in a natural setting. So we present LuckyChirp, a passive opportunistic sonar respiratory sensing with low power consumption for whole day operation. LuckyChirp solves two questions. First, to extract an accurate respiratory rate for potentially moving user. LuckyChirp first detects is the condition good for respiration sensing, which includes is the human present and static enough. And then if the person is static and close enough, LuckyChirp then computes the respiratory rate of the user. There are several challenges in building such a fully passive opportunistic sensing systems. First, continuous mode sonar, such as FMCW, can consume a lot of power because it operates the speaker in always on mode and transmits sound at a high amplitude. Second, sensing time window needs to be short because the user needs to be pretty static during the measurement. However, in practice, the time that a user stays static are sporadic. Third, the sensing range needs to be large. The system should operate with a reasonable field of view to handle real-world scenarios. However, longer sensing distance or oblique angles means lower SNR, which can make respiration detection or estimation more difficult. In order to address these challenges, LuckyChirp employed three novel technique designs. First, we used a correlation-based pulse sonar, which consumes significantly less power than FMCW without compromising sensing accuracy. Second, we designed a novel continuous wavelet transform-based feature extraction. The wavelet transform offers high resolution for a short time window, and thus gives a high classification accuracy. Third, we introduced a novel respiration classification pipeline using a range selecting convolutional neural network, which accurately detects respirations and finds user distance from a low SNR recording. So I'll talk about LuckyChirp sonar design now. First, let's get into how sonar sensing works. The phone or the smart device transmits the sonar signal using the speaker. The transmitted signal are reflected by objects in the environment, including the user's body. The smart device records the reflected signal with its microphone. By comparing the transmitted signal and the reflected signal, we get the time of flight. And we can then compute the distance between the human body and the sonar device by multiplying time of flight with the speed of sound. We can then extract the user's respiratory rate by computing the distance change delta D over time. LuckyChirp chooses a frequency modulated pulse signal for sonar sensing instead of FMCW. Here it shows the difference of LuckyChirp pulse versus FMCW. The orange color is the transmitted signal and the blue color is the reflected signal. Since chirp path only transmits less than the half of the time, FFCW transmit continuously, so LuckyChirp sonar consumes significantly less power. And in addition, LuckyChirp leverages cross-correlation in decoding, which offers a much higher SNR gain than tracking frequency shift in FMCW. And here we shows how LuckyChirp paths get the time of flight. Here I'll show LuckyChirp's algorithm pipeline. We first apply cross-correlation on the received signal and stacked them to construct a 2D waterfall. Then we remove the static reflections from the environment, such as walls and tables, by computing the difference of the waterfall over time and get delta waterfall, whose x-axis is time and y-axis is distance. Then we extract the wavelet scalegram features from each distance and feed the features to the convolutional neural network. The neural network classifies whether it's a respiration or not. If it's a respiration, then it's fed to a respiratory rate estimator. And if it's not respiration, it's disregarded. Here we show the extracted scalegram features from the Sonar. The figure here is an example wavelet scalegram from a respiration signal. It shows a straight line in the scalegram, which corresponds to periodic breathing signal. And the right figure here shows an example from non-respiration signal. It doesn't have a horizontal line in the scalegram, and it doesn't have a periodic breathing pattern. We choose continuous wavelet transform to extract the features because it offers good frequency resolution at low frequencies and better time resolution at high frequencies, which helps detect respirations and motions and helps on classification. We fit the extracted scalegram features into a convolutional neural network model to classify whether the capture sonar has a respiration pattern or not. The CNN consists of 7 layers, and it outputs a binary results of whether the signal has a respiration or not. We randomly selected 460 30 seconds windows of smartphone sonar and manually labeled them for training. During labeling, we plot the corresponding ground truth signals to verify, as shown in the previous slides. Though we only train the model using smartphone sonar, the model is generalizable for smart home devices as well. After classification, we then find the distance between the user and sonar using the CNN as well. We iterate through all the distance. We iterate and feed each scalegram features to the CNN model and let it classify whether it's respirations or not, and continue for each scalegram until it finds the respirations. And the user distance is selected as the one which has the highest probability classified by the CNN of consisting a respiration signal. And then I'll talk about LuckyChirp evaluation. We evaluated LuckyChirp on 2 commercial devices, Google Pixel 4 and Google Nest Hub Max. We conducted over 90 experiments on 20 participants. This results in 320 hours sonar data in total. This shows an example setup of the nighttime sensing. And the phone and smart home devices are put on the table, and in the actual setting, the table may be on the right or the left of the bed. The participant were blanket during the experiment. We use PSG thorax and the under mattress BCG as ground truth. PSG is a kind of sleep study that monitors many body functions, including respiratory activity. The BCG sensor was put on the bed. It used accelerometer and piezoelectric sensors to capture users' respiration. LuckyChirp's respiration accuracy was evaluated by computing the mean absolute error of respiratory rates from sonar to the respiratory rates from ground truth. This shows an example of overnight results from smart home devices and smartphones. The participant was sleeping around 1 meter away from the device. The orange dots are the respiratory rates computed from sonar, And the blue dots and green dots are the respiratory rates from BCG and PSG thorax. The blue line here is the sleep status labeled by a clinician. The results shown in this figure are windows classified as positive by LuckyChirp only. So you can see there are some gaps in the estimated respiratory rates results. Those are the windows that are classified as not respiration by LuckyChirp. It might be because the user moved a little bit, changed their sleep pose to a position where the Sonar device can't detect their chest movement anymore. This shows 29 results from smart home devices and smartphones. LuckyChirp's mean absolute error for smart home devices is 0.5 breaths per minute, and the mean absolute error for smartphone is 1 breaths per minute. We compared LuckyChirp results to a baseline method to evaluate LuckyChirp's classification performance. The baseline algorithm blindly computes all the respirations without classifying it's a respiration or not. And here the figures shows the estimated respiratory rate versus ground truth. The left figure here is the results from smart home device, and the right figure here is the results from smartphone. The comparison between LuckyChirp and baseline shows that LuckyChirp can efficiently distinguish respiration signal from motions and reject wrong respiratory rate measurements. These two figures also show that smart home device captures more respiration than smartphones, which is expected since smart home device has a higher transmitting power, higher sampling rate, and a larger bandwidth. We also compared different sensing window size. We noticed that increasing the window size from 30 seconds to 60 seconds decreases the mean absolute error significantly because larger windows gives more context information. But further increasing the window size to 90 seconds doesn't improve much, probably because the 60 seconds window already contain enough context information. We measured LuckyChirp's actual power consumption compared to FMCW on a Pixel 4 phone. So in practice, LuckyChirp's Chirp Sonar consumes around 67% power of FMCW. And we also measured the power consumption of the CNN component. It consumes minimal power compared to Sonar sensing, as it after processing 12 hours data, it stayed at 100%. We explored several daytime scenarios that LuckyChirp can potentially sense users' respiratory signal. We demonstrated it is possible to opportunistically sense respiratory signals when the user is quietly reading on a laptop or a smartphone, even with subtle interactions on the trackpad or phone screen. The figure on the right shows the corresponding scalograms and the Sonar signal at the specific distance. There is a horizontal line which shows it's possible to capture the user's respiration while reading. For the future work, LuckyChirp is currently designed and evaluated on single user scenarios. We tested that it is possible to monitor multiple users' respiratory rate simultaneously as long as they are reasonably apart. However, it is hard to identify each user is from whom. Each user's respiratory rate. The identification problem may be solvable by classifying users using breathing patterns or body reflection features. We also plan to explore many other daytime sensing scenarios and leverage Sonar to contactlessly monitor other vitals, such as heart rate. So this concludes my presentation today. Thanks for listening, and I'm happy to take any questions.